All right, let's get started again. I know the stuff about the toric code and topological order in the end was a bit quick, and there were many questions during the break. Are there any other, I had this grand plan for LDPC codes, blah, 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 but I think if these are pictures you haven't seen for the toric code and we only get through that, that's also totally fine. So is there anything else I can help explain about the excitations in the toric code, the Wilson loop operators, any of that? Yep.
Can you clarify exactly what you mean by tensionless?
Yes. So think of the Hamiltonian, which is the sum of all star terms and the sum of all plaquette terms, okay? The ground state has all of these terms being happy. So that's the lowest energy state. Now, when I look at excited states, okay, the excited states have some number of charge violations or some number of plaquette violations. The energy of that excited state only cares about how many charge violations I have. It doesn't care about how far apart those charges are. So in this example here, if I act with a single sigma z operator on one link, okay, that's a z error, okay? And what does a z error do? If I act with the z error on one link, I know that it's going to anti-commute with the star operator that lives on this side. It's going to anti-commute with the star operator that lives on this side, but it's going to commute with everything else. So this creates two excitations and has energy 2. On the other hand, if I act with the product of z's on two links, okay, then this star operator is now happy because two things got flipped, and now I have these two charges. But this also just costs energy 2. So I can separate these charges as far as I want, but as long as I have two charges, I have an energy of 2. The strings themselves don't cost any energy. Likewise with the plaquette, likewise with the the X strings which create plaquettes. On the other hand, if you think of this as embedded within some broader Z2 gauge theory, the point is that a Z2 gauge theory, just like electromagnetism has a Gauss law, okay? This is a model of a Z2 gauge theory with matter and fluxes. The matter you can think of as your electric charges, which are violations of your stars. The magnetic fluxes are the plaquette terms, okay? And then charges, here now the bond variables, which are the toric code variables, those are the gauge terms. Okay, so each charge, there's a Gauss law, which says if there's a charge on some one side, the charge is basically a violation of the star term. Okay, so I can now add in tension. So that XL that you see there, okay, that the third term, okay, that's saying that like if I have sigma x on my links, okay, that costs energy. So that's basically driving you to this confined phase, because how do I create charges? I create charges by acting with some sigma x operator. But if acting with sigma x operators, more and more sigma x operators cost more and more energy, then these charges will not want to move far apart. They'll want to stay very close together. Okay? So if I do that, from one perspective, you might think that's great for errors, because I don't make these long winding loops that could give me logical errors. On the other hand, I've also lost my topological degeneracy, because topological degeneracy requires you to be able to take this pair of charges all the way around the loop, bring them back together, and then you get back to a ground state. But if having that entire loop costs a lot of energy, then you're not going to be back to the ground state. Yep. All right. Other questions? Good. All right, so so far we've only talked about encoding information in the ground states of ordered systems, but error correction, of course, is fundamentally a non-ergodic dynamical process. Okay, once you've encoded this information, now you have to think about what happens when you start acting with errors in the system. Okay, errors are going to be exactly this type of term. You can act with sigma x somewhere. That'll create a pair of charges. You can act with sigma z somewhere. That will create, sigma x will create a pair of vortices. Sigma z will create a pair of charges. you now, and if I just think from the point of view of entropy, if you have errors acting on your system, you're just going to leave the code space and you're going to go off into some trivial, much larger space. The code space is a tiny, tiny fraction of the full space available to you. Okay? So the reason this is a non-ergodic dynamical process is because you need to be doing something to your system to keep it in the code space. Okay? So that's what error correction does. I'll tell you two different paradigms for decoding. But this kind of threshold transition, which I think you heard about in Ani's lectures, this basically is a transition that's dependent on, say I have some toric code state, and now it gets corrupted by errors with some noise strength P. Okay? As long as the errors are weak enough, there is an operation that you can do in order to recover your code space. Okay? On the other hand, so what does that even mean here, right? It would mean something like in the toric code, if this is my toric code, as long as the errors are very weak, they'll create some kinds of small isolated quasi-particles, because to create these quasi-particles means I acted with an error here, I acted with an error here, I acted with an error here, I acted with an error here. So as long as they're weak and small like that, you can pair it up and you're fine. Okay? But if they proliferate and you have some long errors all over, okay, lots and lots of errors, well, now I don't know whether the error string looked like this crazy long string or it looked like some other string which wrapped around the system, because there's just so many errors everywhere that I don't know how I should pair these up. And if I pair them up in the wrong way, well, then I'll go around a non-contractible hole and I'll make a logical error. So I lose the ability to decode. Okay? So there's this threshold transition between, in principle, even if you were like the most powerful computer in the world, could you recover the information that you encoded in the system? Or is the information just lost to the environment forever? Okay, so that's this threshold transition between recoverability and non-recoverability. This has, of course, been studied in error correction for a very long time, but an active research direction right now in many-body physics is to think about this transition fundamentally as a phase transition in an open quantum system. Okay, so I have my state. The state has been corrupted by errors. That's what the open means. Okay, and now you have this mixed state, and you want to ask, does that mixed state have some encoded quantum information which you can recover or not? How should we characterize that? What do phase transitions in this recoverability or decodability look like, this information theoretic phase transition, and how is that different from the phase transition in the kind of ground state phases, which has been studied in the type of phase diagram that I drew earlier. Okay, so this, I won't say much about this, but this is a very, very active topic of research right now. Okay, so let's talk about two different mechanisms for quantum memory. As I was saying, the goal of quantum memory is to preserve the code space, and how we do this cares about the nature of excitations in the system. Okay? So in the toric code state, you have some errors that acted on your system. You don't actually know where the errors acted. Okay? All you can do is come in and measure these star terms and the plaquette terms, which is measure your checks. And the violations of your checks are your syndromes. Okay, so those tell you, here is a charge excitation, here is a vortex excitation, and these should not be there in the code space. Okay, so after you've done these syndrome measurements, maybe you'll see a pattern of charges which looks like what I've drawn there on the page. Okay, those dots, those red dots could be violated excitations. Now, I need to take that pattern and I need to figure out, well, what's the most likely, for instance, what's the most likely error channel that could have caused that particular syndrome pattern. Okay? So I'm going to do some classical processing of those measurement outcomes. Okay? And then I can decide, hey, actually if you pair up the syndromes using the error strings that I drew over there, that's a pretty short error string. That's probably more likely the case that's what happened as compared to some other, the same syndrome pattern is compatible with many different error strings. I can take any error string and I can multiply it with stabilizers, which will change what the error string looks like without changing any of the syndromes. Okay, so you have many, many choices. And you can say, well, if errors are rare, this is probably the most likely choice. But at some point, you're not going to be able to do that if there's too many errors, okay? And then once you've decided that you feel pretty good that that's the error that happened, you can apply some kind of corrective operation. And as long as your corrective, the combination of the actual error that happened and your correction does not form a non-contractible loop, you haven't made a logical error, okay? So then you get back to the code space, and then you keep repeating this process, okay? So this is called active error correction, because you need to constantly make measurements of the syndromes, process the measurement outcomes, apply the corrective unitary, and then keep going, okay? And in practice, this is extremely hard to do, because if you have to actually make measurements and then do this very, very non-local processing, because again, these charges are deconfined, so in principle, your error strings can be quite long, okay? So you need to figure out non-locally where these strings can be, and then apply this non-local feedback operation. As a practical matter, that's actually quite hard to do, okay? What you would much rather do is do passive error correction, and passive error correction is information protection, not from this kind of constant processing of information. Okay, every time I'm making measurements and doing feedback, I'm sucking entropy out of the system. And that's how I'm keeping my system in the code space. Okay? It would be really nice if I didn't have to do all of this work. Let's say I could just keep my system coupled to some cold enough reservoir, some cold enough bath, okay? And then I would have my memory being protected. Okay, this is of course how a magnetic hard drive works. Okay, your system, as long as it's at a low enough temperature, is just magnetized. Okay, and because it's magnetized, it's preserving the up and down magnetizations that you're encoding in your bits for a time which is like the age of the universe. You then don't have to go in and further do all of this processing to make it work. Okay, so passive memory comes conventionally from thermally stable order, and again, the simplest example of that in the classical setting is the two-dimensionalizing model, or in a hard drive, the three-dimensionalizing model. If we are talking about the two-dimensionalizing model, then I have two ground states, which is again the all up and the all down, related by symmetry breaking, but there's actually a ferromagnetically ordered phase below a critical temperature, which is Tc. Okay? So everywhere below the phase, I have not just below this temperature, I have not just the all-up state, but I have the all-up state dressed by some thermal excitations, and I have the all-down state dressed by some thermal excitations. Okay, but these two states, these two mixed states dressed with thermal excitations, they're two symmetry-broken equilibrium states. These are separated by some macroscopic free energy barrier. Okay, so this is like Landau series symmetry breaking. So if I start in the all-up state, and you think of coupling it to some heat bath at some temperature below Tc, the bath will do what's called Glauber dynamics. You can just think of it as like, you either flip or don't flip with some metropolis probabilities. You'll find that you get a mixed state, okay, at some temperature below Tc, but that mixed state looks mostly up for some time that diverges with system size, okay, that's set by the size of the free energy barrier. Okay, so as long as I'm maintaining this cold enough temperature, I don't need to do any further active error correction. Okay, so again, the philosophy is just code states are ground states, errors are excited states. How do I go from excited states back to ground states? If I have thermally stable spontaneous symmetry breaking, then the spontaneous symmetry breaking itself gives you a kind of non-ergodicity, because it's giving you these two macroscopically different stable states, which are going to remain preserved for some diverging lifetime. Okay? So then the errors, they don't proliferate. They're going to remain kind of bounded. Okay? But the point is that this 2D-izing model is in 2 dimensions, and the reason it has a stable ordered phase is because it's in 2 dimensions. If I was just in 1 dimension, then Peierls will tell us, Peierls theorem, that we don't have a stable symmetry broken phase at any finite temperature. Okay? And why is that? It's again because of this feature of deconfinement of excitations. Okay? In the 1D-izing model, what do my excitations look like? They look like domain walls. Okay? Domain walls here are point-like. Okay? There is a domain wall separating an up and a down spin. But I can separate a whole bunch of down spins instead of just one. I'll have a domain wall again. Okay? And this far separated domain wall costs no extra energy compared to the nearby domain wall. Okay? So there's a lot of entropy to be gained by having your domain walls run around freely at no extra energy cost. So if you look at free energy, which is E minus Ts, in one dimension, the entropy always wins, and at any finite temperature, you have no ordered phase. There's only a ground state phase. So now, much like the toric code, if I wanted to do classical error correction with the 1D repetition code, okay, then I would have to do this active process. I would have to keep measuring where the domain walls are and keep trying to do some non-local processing to pair them up. On the other hand, if I'm in 2D, then my domain walls are not point-like. They're actually loop-like. Okay? And now these are confined because if I make some domain of flip spins bigger and bigger, the energy that it costs increases with the size of the domain. So it costs more and more energy. So now I can have an energy entropy trade-off, and below TC, it's actually going to be very costly for me to make these big domains. So I'm going to stay mostly near the all-up state, okay, or the all-down state. So below TC, I can do a passive error correction, where as long as my temperature is maintained below TC, I'm going to retain my memory. Yeah.
Could you reiterate the Glauber dynamics? I wasn't fully sure why that got referenced, or why it's used, or why it shows up.
Oh, Glauber dynamics is just a way of saying like, so you have to do some measure correct feedback process to maintain your system in the code space, okay? Or maintain your system in a space from which the code space can be easily recovered. So one version of that, which is the active error correction, is like I measure all the syndromes, process it, do some non-local big correction operator, and I keep doing that over and over again. That requires this non-local active feedback. Passive dynamics is just what would nature do if you had an Ising model coupled to a cold bath, okay? That's local detailed balance obeying dynamics.
Which is Glauber.
Glauber is an example of that. And that's just, you flip or spin or not depending on its immediate neighborhood, okay? There's actually a lot of recent work on quantum Glauber dynamics, which is much more subtle, but fine. But the principle of it is just, you're just looking in your local neighborhood and you're deciding what to do based on that. So that's passive, yeah.
Thank you.
Mm-hmm. Okay, other questions? Yeah.
How does the size of the energy barrier between the two states relate to like the distance and the threshold of the quantum memory?
Good. So it doesn't. So 1D Ising model and 2D Ising model, that's a great question, because for 1D Ising model and 2D Ising model, K is 1 for both. There's one logical bit. And D is N for both, which is how many bits do I need to flip to go from one ground state to another. So K and D alone do not tell you about what type of error correction you will need to do. Okay? The threshold theorem just tells you that as long as D is diverging with system size, there is some process, some error correction protocol that you can do, which will recover your state. It doesn't tell you how local that is. It doesn't tell you whether that has to obey detailed balance or not. It doesn't tell you what that correction looks like. So just doing repetition code, if I arrange my bits in one dimension, then my domain walls are point-like. I can make an arbitrarily large domain and only pay an energy cost of 2 for the endpoints. And to actually be able to keep myself in the code space, I have to do this active error correction prescription where I need to see how do I pair up my domain walls. Okay? On the other hand, if I just do the repetition code, but now I arrange my parity checks in 2D, and I arrange my bits in 2D, well, then making a big domain actually costs an increasing energy, so that's going to be more costly, and your domain walls will have this tension, okay? And the tension causes them to not want to proliferate, so then I don't have to do this costly error correction prescription in order to preserve memory.
So I guess like
Exactly. Yeah, exactly.
But we can't see that in some code parameter.
No. That has to do with the energy barriers of the codes. It's much harder to calculate. But just K and D does not tell you what the energy barrier is. Yeah. OK, good. So now let's talk about this for the quantum models. OK, and now to get quantum topological order, first of all, I need 2 dimensions at least. There are no quantum codes in 1 dimension. I need this large code distance for both x and z. OK, and now if I'm looking at 2 dimensions, the 2D toric code, then much like the 1D Ising model or repetition code, if I have some excitations, they can be arbitrarily far separated without any extra penalty. That's the deconfinement. And in fact, for topological order, the deconfinement is necessary, okay, in 2 dimensions in order to get this kind of topological phase. So now I have these charges, and these charges are getting, to separate the charges, I need to pay this. I don't have to pay any extra penalty. So that's why to do error correction, I actually end up with the need to do active error correction, okay, which is, again, costly. On the other hand, if I want my electric and magnetic fluxes to cost some energy, okay, while still maintaining the topological order, the only way that this can be done, so you want to have electric flux loops which cost energy. You want to have magnetic flux loops which cost energy. And in order to do that, you actually need to go to 4 dimensions. Okay? So if you want a passive, stable quantum memory, then the only known example of that which we have is the 4-dimensional toric code. Okay? And of course, we live in 3 dimensions, so there's been a lot of work in trying to build passive quantum memories in 3D. The whole field of fracton physics got started with that motivation. Okay? But as far as we know, so far, there are no known examples in 3D. Okay. And actually, even though these problems looked quite separate, on one hand, I was talking about classical models, and the other hand, I was talking about quantum models. I promised you at the beginning that if you really understand classical codes, you'll be most of the way there in understanding quantum codes. And that's through this formalism called product constructions. Okay? And these product constructions actually reveal a very, very deep relationship between classical codes and how you can take different classical codes and use those to build up quantum codes. So in fact, you can take 2 1D Ising models or repetition codes and take what's called a hypergraph product of these codes and get a toric code. And this hypergraph product, the nature of the excitations, the symmetries, the redundancies, all of those features about the classical codes are inherited by the quantum code. Okay? So the fact that the toric code has point-like excitations directly comes from the fact that the 1D Ising model has point-like deconfined excitations. Okay? And that's why, because I need to do active error correction for the 1D Ising model, I need to do active error correction for the 2D toric code. Okay? Just as an aside, I'll say that there's a big research area. So, you have active versus passive, which you can view as like detail balance obeying versus not. But then you also have local versus non-local. Okay? And experimentally, non-local decoding is a much, much bigger challenge. Okay? So there's a huge research effort in trying to build local non-detail balance obeying or local active decoders for classical codes in 1 dimension, okay? Which would then predict local active decoding for the toric code in 2 dimensions. Okay, so this is an area where lots of work is happening. Yeah.
So in 4D toric code, why do you want confined flux loops? Shouldn't we be looking for deconfined excitation?
Good. So there's yeah. So it gets more subtle. Like you can. There are membrane operators which are tensionless. Okay, so think in 3D, actually the 3D gauge theory, the 3D classical gauge theory is a good example. So you have like plaquette terms, but now they live in 3D. And what it looks like is you have a membrane operator. The membrane can fluctuate as much as you want. And the edge of the membrane is a flux loop. Okay? So, but it's the membrane which is like the analog of the logical. And the flux loop is the excitation, which is the analog of your two charges. Do I have another marker? Yeah, good. So in the 2D toric code, I had charges which cost energy, separated by a tensionless string. In the 3D gauge theory, I have a loop which costs energy, a flux loop, separated by a tensionless membrane which can fluctuate as much as you want. And by the time you go all the way around the system, you basically stretch out a big membrane, which is like stretching out this big loop. Stretching out the membrane doesn't cost, this part doesn't cost any energy. But then you take the flux loop and you bring it back together, and then you're back to a ground state.
Okay, so the membrane is free to move.
The membrane is free to move. And the different ground states differ by a membrane operator, which doesn't cost energy. But to create that big membrane operator, to create it in the first place, just like to create this big string operator, here I had two endpoints of charges. Here I needed an endpoint of a loop. But a loop is good because that costs more energy. So,
Okay, thanks.
yeah. Okay, good. So now I'm going to write down a web of connections, okay? So if I take two 1D Ising models with spontaneous symmetry breaking order, okay, and these deconfined domain walls, and I take their hypergraph product, this is a construction in the coding literature, then I get the 2D toric code with topological order. Okay? And again, the physical properties of the Ising model are inherited by the toric code. The reason that the toric code requires active error correction is the same reason that the Ising model requires active error correction. The reason the 2D toric code does not have thermally stable topological order is the same reason the Ising model in one dimension does not have thermally stable symmetry breaking order. Okay, so there's this deep relationship. In trying to unpack, and these product constructions are used heavily in these constructions of good codes. Okay, so in trying to unpack those good codes and what the product constructions mean in that language, what we realized is that you can really think of the hypergraph product as equivalent to a different prescription, which from the perspective, again, of condensed matter physics, at least gives me more intuition, which is that I can also take two 1D Ising models, and I can take what's called a tensor product of those 1D Ising models. Okay, the tensor product is not making anything quantum. It's just like the simplest product you can imagine. So you'll go from two 1D Ising models. I guess I should have drawn this as horizontal and vertical. That would have been a better drawing. So if I take it as two 1D Ising models, horizontal and vertical, I take the hypergraph product, I get the 2D toric code, I take a tensor product, I just get the 2D Ising model. Okay? The 2D Ising model obviously again has spontaneous symmetry breaking order, but the 2D Ising model also happens to be the gauge dual. The paramagnetic phase of the 2D Ising model is gauge dual to the 2D toric code. Okay, so I'll explain what gauging is if I get time, but gauging is a way to take global symmetries. In the 2D Ising model, I have a global Ising spin flip symmetry, and to promote those global symmetries to local symmetries, like local Gauss laws, by introducing extra gauge fields. This is what electromagnetism does. This is what anytime you study gauge theories, you say that you have some like local freedom of choice in the description of your system. That's your local gauge freedom. And you need some gauge fields to mediate how different locations in space are going to be related, given that each location in space has this local gauge freedom. Okay, so you can take the 2D Ising model. The Ising gauge theory is introducing gauge fields to promote that Ising model to a gauge theory. Okay, and when you do this gauging prescription, excitations of your original model end up being the dynamical degrees of freedom in the gauge theory. So for the Ising model has domain walls, And under gauging, these domain walls become the flux loops of the gauge theory. Okay? So that's why when I do the gauging, it's the paramagnetic phase of the Ising model in which my domain walls have completely proliferated. So again, I have this loop soup of deconfined domain walls, which end up converting into the loop soup of electric and magnetic flux lines upon doing this gauging. Okay? So the point is that when I want to get this 2D topological order, you should really think of it as you're building an appropriate 2D classical code. Again, I just like classical codes. I'm simple-minded. You should think of it as you're building an appropriate 2D classical code, which, upon gauging, will have the properties that you want from your topological order. Yeah. Why am I mapping it to electric and magnetic flux? This is just standard, like if you know, gauge theories were first developed in the context of electromagnetism. There you have electric charges and electric flux lines and a local Gauss law. When people first wrote down Z2 lattice gauge, so that was like U1 electromagnetism is a gauge theory. Then in the sequence, people said, okay, let's think about lattice gauge theories. You know, that's just something, again, people did in the 70s. And now instead of having a U1 gauge theory where, you know, you have a U1 freedom on each side of e to the I phi for your wave function, you can think of a Z2 lattice gauge theory, okay, where you just have charges and you have some local Gauss law. But now your charges are Z2 valued, you know, either a charge is present or not. And your electric fluxes are Z2 valued, either it's present or not. Magnetic fluxes are Z2 valued. So again, Z2 lattice gauge theory was something developed in the 70s. It has this deconfined phase. It has this topological phase. And then Kitayev's insight was that you can take this topological order, which had been extensively studied in the context of gauge theories. And Z2 is useful there if you're thinking about qubits and so on. And you can, like, you know, like, again, Z2 gauge theory was written in the 70s. Kitayev's toric code was written in the 90s. These days, when we studied the toric code, it's just like, here's this model. It came out of thin air. But you know, it didn't come out of thin air. The reason it has the properties it does is because of the topological order of Z2 lattice gauge theory.
But it's not related to like how you implement error correction codes.
No, it's not related to. I mean, you don't have to. You can think of it as vertex violations and plaquette violations without calling them electric and magnetic charges, and that's fine. Yeah. Mm-hmm.
How should I think about the number of conserved quantities I would have when there are certain symmetries present, like Gauss's laws here? How are they related to, I suppose, the number of qubits I'm encoding? How is that related to N and K and D? Because LDPC codes have a certain bound on how N and D.
So you should think of the gauge theory as having lots of local constraints. So these are local symmetries, okay? So your local symmetries, like the star term, because each star term commutes with the Hamiltonian, you can just think of each star term as a local Gauss law, which is what it is when you couple it to matter. Likewise, if I work on not the square lattice, but the dual square lattice where every plaquette has a site, and you know, so then these terms look like local Gauss laws. It's just equivalent, okay? So you can think of this as like, the toric code is built up of a bunch of local Gauss law terms. They all commute with the Hamiltonian. So I have a choice where, like, I can decide that my code space is going to be some crazy pattern of violated checks. Or I can just decide, like, I'm going to enforce Gauss law everywhere. Okay, so if you enforce Gauss law everywhere, then all of these constraints are happy, all of these constraints are happy. These are your local constraints. That defines your checks, because you want your checks to be local. And then, like, your code space is just like how much freedom do you have left after you've specified all your Gauss law constraints. Yeah. Okay. Something I won't talk about is that there's also another way to prepare toric codes, which also has to do with phases of matter, and this is intimately tied to measurement-based quantum computation, okay, where you start with cluster states on a different lattice. This is now the Lieb lattice, where you have degrees of freedom not just on the bonds, but also on the sites. Again, if you're thinking about gauge theories, you want to think of degrees, you know, charges living on sites and gauge degrees of freedom living on bonds. So this Lieb lattice, again, appears quite naturally. If you write down a cluster state, you can write down cluster states for any graph. If you write down a cluster state for this Lieb lattice, that ends up having what's called symmetry-protected topological order. And now you can measure out half the degrees of freedom in that cluster state, and that gives you another way to get back the toric code. Okay, so a lot of these protocols, almost every protocol that I know, which does measurement-based quantum computation, a lot of the works by Rausendorf and his collaborators, all of those papers basically start with some kind of symmetry-protected topological order. There are all sorts of relations, again, in condensed matter theory about if I have a symmetry-protected topological order in 3 dimensions protected by higher form symmetries, then the boundaries of those have to break the symmetries. In this case, the RBH cluster state in 3 dimension has to have toric codes as their boundaries. This is, again, a principle of condensed matter physics. And now as you start measuring this RBH cluster state, you can teleport the information from one boundary toric code to another boundary toric code. So again, I definitely won't have time to talk about this, but a lot of the principles of measurement-based quantum computation, again, come from physical principles of topological order and all of this web of relations between what kinds of topological orders and symmetry breaking orders are compatible, which orders can live on the boundary of which other type of order in one higher dimension, but piecing all of this together kind of gives you this, this web of connections. Okay. All right, so, okay, so I'm very, very far behind on time, but okay. So the plan was gonna be to now talk about these good LDPC codes and expander graph and understand them in the same kind of physical picture that I mentioned in this slide. Okay, so in particular, the question that my collaborator Tibor Rakowski and I have been asking for the last couple of years is how do we understand the physics of these LDPC codes in the similar language that I've been describing to you, okay? And basically, what we've shown is that you have a similar kind of phase diagram that you can make for these LDPC codes, where one corner of it is the LDPC code, much like the toric code, which extends into a full phase. This is a very weird kind of topological order. There's some local indistinguishability that is present for sure, but the, K is proportional to N. There's also lots of details that care about the lattice geometry, similar to fracton models. Okay, we've talked about how do you formulate classical LDPC codes, a symmetry breaking order in this context. How do you think about SPTs? How do you think about these dualities, these gauging dualities, which take you from classical codes to quantum codes? And how do you think about the SPTs that you can measure in order to get the quantum codes? Okay, so all of this entire philosophy with some work can be ported over to this QLDPC context, and these are all generalized Z2 to the K gauge theories. And then, you have to ask a very natural question, which is if I want to start thinking about these as phases of matter in order to, then it better be stable to perturbations, right? Like a single point does not define a phase of matter. A phase of matter is something where I can come in and I can add all sorts of perturbations. That's the phase diagram I was showing you for the Z2 lattice gauge theory, that I want to add all sorts of perturbations and it should extend into an entire phase with those properties, okay? But all the theorems that we had on phase stability, all of like the ones I was mentioning from Hastings et al., all of those were developed again for local Euclidean models. So a question you want to ask is like, well, if you have this degenerate ground space manifold separated by a gap, usually gapped phases are thought to be stable. So if I take this LDPC code, view it as a Hamiltonian on some general graph, and add a perturbation, well, is the phase going to be stable? Is the ground state degeneracy going to be stable or not? Okay. So this kind of stability question, which is generalized Hastings, we worked this out and we showed that in fact they do correspond to stable phases as long as you act with weak enough graph local perturbations. And this is already very weird from the point of view of the third law of thermodynamics, because if you have K proportional to N, then you have exponentially many ground states, which is a finite, or which is an extensive ground state entropy, T equals 0 entropy. Usually when you have this, you expect that as soon as you add some perturbations, the ground state degeneracy gets lifted. You don't have a stable violation of the third law of thermodynamics, okay? But again, all of these heuristics were developed with Euclidean systems in mind, where boundary and bulk scale in a particular way. In fact, here you can add weak perturbations on the graph, and you get a stable phase with extensive ground state entropy. Okay, so that's quite strange. Then you can ask, similar to what I was saying about active and passive decoding, what is the nature of memory in these expander LDPC codes? And what we uncovered, which I will present in the seminar tomorrow, is actually, we know that these models are passive decoders, but as far as their thermal properties go, the properties of this phase, not just in ground states, but at finite temperatures, in many ways, thermally, they don't look like they have thermally stable order, topological order in some conventional sense. But what we showed is actually this should be understood as a very new type of spin glass order, which is a topological spin glass. Usually, spin glasses have been widely studied in physics as a way of encoding classical memories. There was no topological analog to that was known, but actually thinking about these QLDPC codes revealed that you can have a topological analog to a spin glass, which allows you to store quantum memories in a very interesting way. So I'll present that tomorrow. Okay, so let's now move on and start talking a bit about classical expander codes. Okay, so I'm going to go back again to classical models, okay? And what is an expander code? An expander code has the following defining property, which is, suppose you start in a code word, which can be the all zero state is always a code word. Remember back to the parity check matrix. And now you start flipping some number of spins. An expander code has the property that as long as the number of bits flipped is less than some finite fraction of all the bits possible. Okay, so delta is some number less than 1, and delta times n means that I go in and I flip like a finite fraction of all spins, let's say quarter. Okay, and as I flip all of these spins, the energy cost that I encounter, which is how many stabilizers did I violate, the energy cost scales linearly with the number of spins flipped. Okay, so this is a linearly growing extensive energy barrier. In particular, this already tells you that the code distance has to be proportional to n, because the code distance tells you you have to get back to a code word. Okay, but as long as you flipped some finite fraction of spins, you have an energy cost which is kept growing. Okay, so you can't come back down to 0 without going through this big energy barrier. Okay, this should be really weird to you from your Euclidean intuition, because in Euclidean space, this is for any set of bits that I flip, the number of checks violated scales proportionally to the number of spins that I flipped. Okay, this is very different from Euclidean space, because again, come back to the Ising model. If I flip some big patch of spins to go from the all up code word to the all down code word, the energy cost that I pay only scales with the perimeter of the spins that I flipped. Okay, so that's a boundary cost, which is parametrically smaller than the bulk cost. But in these expander codes, the energy cost scales with the number of spins flipped. So expander codes require expander graphs in which boundary and bulk scale proportionally, although this is a necessary requirement and not a sufficient requirement. Okay, you need to do some extra things. So coming back to Sharon's question, I need an expander graph both to get good codes in which k and d are proportional to n, but also to get this additional property of energy barrier structure. Okay, so I already told you an expander graph, that's a hyperbolic tessellation. That's this locally tree-like model. These are models in which boundary and bulk scale proportionally. There are many examples of these. A very familiar one is what's called a random regular graph. You can also have Cayley non-random examples, look like Cayley graphs of certain non-abelian groups. You can do tilings of the hyperbolic plane. So there's different ways to get these types of graphs, okay? And now there are, again, multiple approaches for building good classical LDPC codes. The first example comes from the PhD thesis of Gallagher, as I was saying. This is the simplest possible LDPC code you can write down. It basically says to take an m by n random sparse parity check Hamiltonian. Okay? So it basically says each check should act on C bits, where C is finite. So the sum of ones in the row should be C. It says each bit should be acted on by B checks, or each bit should be part of B checks. So the sum of every column is B. B and C are both order 1. Other than that, the matrix is sparse and it's random. Okay? And actually, if you just do this construction, you can show that with high probability, H has full rank, so there's no dependencies between your checks, and that it's a good code if B is less than C. So you can do a constrained counting, and you can do some things, and you can do this. Okay, so this actually ends up being a bi-regular random regular graph. If you think of this Tanner graph where you see which bits are acting on which checks, you know, the bits have some fixed degree, the checks have some fixed degree, and other than that, they're random, and this gives you a good classical code. Super simple. Okay, a more kind of physicsy model comes from what are called Tanner codes. So this was Sipser and Spielman in the 90s. Okay, really talked about this family of codes. In this model, you first start with an expander graph. By the way, I'm drawing these very simple pictures of degree 7 expander graphs. Okay, the proofs for these models are on much, much more complicated expander graphs, which have degrees of 100. But in doing this kind of, or hundreds or thousands, but finite. But in doing this kind of work on glasses that I was telling you about, we actually did numerics on the simplest non-trivial models you can write down, which are these degree 7 graphs, and we found like it actually looks very good. Okay, so not a proof, but that's why I'm drawing these pictures. So for Tanner codes, you start with such a graph, and now you decorate it. The way you decorate it is to say that, okay, in my classical code, I'm going to put bits on all the bonds. And then for every vertex, I'm going to put what's called a small code, which is a code which only acts on the bits that are incident on that vertex. Okay? So here I have a degree 7 small code because I have a degree 7 graph. And I can put down this Hamming 743 code that I had shown you earlier, which acts on the 7 bits adjacent to that graph. And that same code is now repeated everywhere. And the checks of the global code are the collection of checks of every one of these local codes. Okay? So now this is manifestly local on this graph. So it's manifestly LDPC. And now you can show that as long as your graph is sufficiently expanding, there's various ways to quantify the expansion of the graph. And as long as the good code, the local code, is sufficiently good, okay, this is why you need these very large degrees in the proofs, then you can prove that this model is also globally a good code. Okay? To give you a piece of intuition, why do these models give you these good codes? Let's think about how we would go from one code word to another. Okay, so these are just pictures of what you should have in mind for what these models might look like. So if you start from the all zero state, this is a code word, as we said. Now, let me flip one spin. If I flip one spin, I may make 2 of these local codes unhappy, because the local codes were Hamming 743 codes. So the smallest number of bits I have to flip to make the local code happy again is 3, because the code distance of the local code is 3. Okay? So these 2 are unhappy, but I flip 2 more bits, and now the local code in the middle is happy. Okay? But now I've spread the pain, because now I have these 3 other codes which are unhappy. So I need to flip some other checks before those become happy. And now I need to flip, and I need to keep doing this. Okay? So this also tells you why you encounter these big energy barriers, because you start from some code, you start trying to flip it, and you have to encounter this big cost before you can start becoming happy again. So now where does the large local code distance come from? Well, we have to flip many bits around each vertex if you have a large local code distance, which means globally, you'll also end up needing to flip many bits globally to become happy. So this large local code distance can translate to a large global code distance. Likewise, if you have a large local code rate, that means you have many choices for how you satisfy the local code. So on each vertex, you can tile a choice from this local code with a choice from this other local code with a choice from this other local code. And that on net gives you many global possibilities to satisfy the code as a whole. Okay, so Sipser and Spielman's work was really showing how these local properties of the small codes can get broadcast through this expander graph structure to the global properties of the full large global code. Okay, so these are the actual conditions that you need on the local codes for getting the global code to be what it is. Okay, so what this means is that, this kind of algebra, I've shown you how, I've not shown you, or at least like illustrated for you the steps that are involved in going from k equals 1, d equals n, which is the 1D Ising model, to k and d both proportional to n on this expander graph geometry. Okay? So great. Now, as I said, these good classical codes were already developed in the 1960s and 90s, and there was this huge gap in getting to the good quantum LTPC codes. Okay? So what was the missing structure? To get into that and to figure out what we need, I'm going to give you a little primer on baby kind of homology theory, which is kind of a unified description of all quantum CSS codes. So this includes the 2D toric code that we talked about. It includes all of these fracton models, and it actually includes codes in any dimension or any manifold, Euclidean or not. And the key punchline is that your code is going to define a notion of geometry through this mathematical concept called a chain complex. And the notion of geometry and the dimensionality of that geometry can be completely different from the geometry of the underlying lattice. Okay? And it's this code geometry defined in terms of the chain complex which sets the relevant properties. Okay. I have like 15 minutes, right? I'm 5? Oh, really? Okay. Even though, okay. All right, fine. Okay, let's see. Okay, maybe I'll get to one punchline. Okay, so let's go back to classical codes. Okay, we already talked about how our bits and checks define vector spaces. Okay, and the parity check matrix is a map between these vector spaces. So if I look at the transpose of the parity check matrix, that's a map from checks to bits in the support of the checks. Okay, so if I act on a syndrome vector with this delta 1, which is the map, then I know what are the subset of bits in the support of the checks that I selected. And the converse is if I act on some configuration of bits with the parity check matrix, then I'll know which syndromes are violated in those bits. Okay, so there are these maps that go back and forth between the bits and the checks. Now, a quantum code actually comprises 2 classical codes. Okay, there's the HX and there's the HZ. So if I just think of 3 vector spaces now, one associated with the qubits, one associated with the Z checks, and one associated with the X checks, okay, then I have an X-type parity check matrix, which is a map from the vector space of X checks to the vector space of Z check, or qubits. And then I have a Z-type parity check matrix, which is a map from the vector space of Z checks to the vector space of qubits. Okay, so that's what that is. And now you can say, well, I mean, you already did all of this work to figure out good classical LTPC codes. So can't I just make HX and HZ both good, and then I'd be done, right? So what's the problem with doing that? Why did it take 40 years? Well, because you need HX and HZ to commute, okay? If you want to make this a quantum code, then HX and HZ need to commute. And if you end up picking a good, let's say we pick a good CZ, okay, and a good Cx, then what's a good Cz? If I need Cx to commute with Cz, okay, then every check which is telling me where Cx acts is like a code word for the Cz code, right? Like in the toric code, I had my plaquettes, okay, but every configuration with just these 4 spins flipped, which was the X term, is a small code word with respect to the Z code because they commute with each other. So if the CZ code is good, okay, that means that it has very, very large code words. So if I want to make those code words, if the CXs have to include those code words, well, then the CXs can't be local or LDPC, and then the LDPC condition is violated. Okay, so in order to satisfy this commutation property, I need a condition between the maps here, which is that the composition of the delta 1 and delta 2 maps gives me 0 mod 2. What is this telling me? Delta 2 is selecting out a particular type of Z-check, and it's telling me which qubits is that Z-check acting on. And the delta 1 is saying, if you act on those qubits, which X checks are triggered, okay? And you want no X checks to be triggered. So you need the map to have this composition property, and sequences of vector spaces which have this composition property are called chain complexes.
Sorry.
And there's a
Could I ask a quick question? So if you choose CX and CZ to be the same, it corresponds to like a weakly subdual CSS code. So it would still satisfy the duality condition. So why does that not work? If you choose CX to be a sparse,
right,
it's corresponding to a classical LDPC code.
No, but if you choose CX to be good, so remember, you can write the parity check matrix, but in one case you're going to put X's in all the ones, in the other case you're going to put Z's in all the ones. Mm-hmm. So if CX is a good classical code, then its code words have to be very big. Mm-hmm. And then its code words cannot be, its code words cannot be the Z checks, which also have to be code words for your classical X code.
Okay.
So if you choose them that way, they won't commute with each other. Either they won't commute with each other or they won't be good. Okay. Yeah. Okay. So a chain complex is a sequence of vector spaces with linear boundary maps. So you can have any big sequence, V0, V1, V2, all the way to VDC. Okay. And then what this condition is telling you, the defining condition is the composition of these subsequent maps gives you 0. And this means conceptually that the boundary of a boundary is 0. Okay? So if I start with the plaquette, if I look at all edges that are part of the plaquette, those are 4 edges, and then I look at all vertices that are part of those 4 edges, mod 2, then I get nothing. Okay? So the boundary of a boundary is 0. Homology theory is the composition of topology, which is some cellulation, and group theory, which for us is this F2 space. And the big kind of insight in constructing these good codes is that you need to build up, even though you are in infinite dimensions, you can actually be morally only a one-dimensional chain complex. Okay? I won't have time to explain this, but from the point of view of classical codes, a higher dimensional chain complex is one in which there are many, many local redundancies. Okay, like a 2D classical code has many local redundancies having to do with the plaquettes. So I need something like a plaquette-like structure. Okay, and the code itself has to have that kind of plaquette, even if just the graph having plaquettes is not enough for the code to have plaquettes, which I can unpack if you ask me a question. But basically, the point is that good classical codes are one-dimensional chain complexes. And to build a good quantum code, we need to go to some algebraic structure which is morally two-dimensional. And this requires taking these kinds of product constructions. So products are really a way of building up 2 dimensions from lower dimensions, much like you can think of taking a product of 2 circles and getting something like a torus out of it. Okay, so that's the kind of underlying principle behind these types of constructions. I have 50 more slides, which I'm not going to get through. But okay, you can ask me questions if you want. All right.
So I have two somewhat related questions. Yeah. One was when you're building the quantum codes from these two classical codes in this way, you mentioned like some of the features of the classical codes get inherent in the quantum codes.
Yes.
Like what can we say about the gates that are present in the quantum code from the gates that are present in the classical code, if anything? So that's question one.
Okay. For the inheritance of gates, I don't know. Yeah.
Okay, and then this might be naive, but so here we've taken these two classical codes and we built this 2D picture. And from this 2D picture, we, I guess, uniquely define a quantum code. Now, could we now go and do this with, say, 2 quantum codes and get like a 4D picture?
Yes.
And like some subset of that be a quantum code? And
yes, exactly. And that is how you would build up the 4D toric code, for instance.
I see.
You can take a hypergraph product of 2D models, which would give you something in 4D. And then that's a bigger chain complex. And that's what gives you the extra kind of properties having to do with the passive correction.
I see. And then in that larger 4D space, do we now have to make some type of like choice of, because that's more dimensions than we had before to define a quantum code? So are there multiple codes within there that we now choose?
Exactly. And in fact, like depending, so if this is, basically you should think of these different levels as vertices, edges, plaquettes, cubes, hypercubes, hypercubes, and so on, which is like a cell. If you were just coming up with this description for a regular manifold, this is what it would be. But there's like basically you can use the check structure and you can think about hyper edges and so on to write this. But for the 4D toric code, I would have 5 levels, 1, 2, 3, 4, 5. And if I occupy the middle 3 levels from my code, then both X and Z type checks will be loop-like and I would get the self-correction that I want. But if I occupy these 3 levels, I always need 3 to define a code, 3 consecutive ones. If I occupy these 3 levels, then only one type of check is thermally stable, the other one isn't. So then it's a classical memory, passive, and not a quantum memory. Yeah.
We'll take one last question.
There are these subsystem error correcting codes where the checks don't commute. So does this formalism hold, and can you create these good quantum LDPC codes in that context as well?
So we thought a little bit about this, not enough that I can give you an answer at the top of my head. Yeah.
Thanks.
Yeah. Okay.
Let's thank the speaker again.
Okay.